Okay, so let us start. So we will continue discussing about search. So last class uh, we gave a general discussion about search. So we consider goal-based agent, and you remember in chapter 2 we learned different kinds of agents. Okay. And here about the environment, it's fully observable and deterministic, discrete, knowing environment. And last class, we discussed if you recall, when we discussed the search, we said we consider frontier and explore that. Okay, so this is a quick review of the last class. And I think I need to close this slide and then start with a new one and then to share screen. Okay, so today we will focus on discussion about different search strategy. And we will start with the uninformed search strategy. Uninformed search strategy. So search strategy here says it's defined by picking the order of nodes to expand. You remember last class we also discussed like depth first search, breadth first search. The order of node to expand is different. So we will discuss this. Uninformed search strategy, it only uses information available in the problem definition. So this is for uninformed search. And last class, we discussed the breadth first search, depth first search. Both of them are under this category. So it's uninformed search strategy. We will also look at iterative deepening search, what that is, and the uniform cost search. So this is just general idea. So first, let's take a look about the breadth first search. So what is breadth first search? So if by tree, we know it's level by level. Okay, so it said expand the shallowest unexpanded node. And the structure you used to store nodes, we use queue. So first in, first out queue. So frontier is a first in, first out queue. Okay. So here it gave us an example about the breadth first search. And last class we discussed that for the search state space, we can abstract it using graph. And for the graph, then we have vertices, we have edges. So the node represents a state. So you transition from one state to another state. So generally here, when we discuss, so we don't mean it's always like you do route search. It can be applied in other situations. Okay, so generally consider it's a search. So breadth first search, then in this regarding first. So just to remember, it's expand, shallow is unexpanded node first. Shallow is unexpanded. So let's take a look of this example. So the starting state is S, and G is the goal state. So you want to find an optimal path, you think, that will lead you from starting state to the goal state. So for breadth first search, so you will put S first in the frontier queue. So at the beginning, frontier queue only has S. And then you first in, first out, you want to expand, so you take this S out. And you add 3 nodes. It's 3 neighbors. So who are the 3 neighbors? D, E, and P. So you add D, E, P in the queue. That's how you come to the second level. You add D, E, P in the queue. Okay, assuming the order you add is D, E, P, then the first node you are going, so right now in the frontier, you have DEQ or DEP. So the first node you will expand is D. So you will get D out of the queue. So D, who is D's neighbor? It's BCE. So you will add BCE to the queue. Okay, to the queue. And what's the next one? And then you go to E. So you take out, because in the queue, the first element in queue is E. You get E out. And you add E's neighbor. Who is E's neighbor? It's H and R to the queue. So now, what are the elements in the queue? At this point, what are the elements in the queue? Who is the front node in the queue? At this point, after I expand E, who is the first node in the queue? It's P. Yeah, it's P. Okay. So then you expand P. P, who is P's neighbor? The downward link, it's Q. So now in Q, what are the nodes in the queue? After I expand P, who are the nodes in the queue? It's all of the green level. And that also, so you can see the breadth first is level by level. So expand the shallowest level first. So next it will go to B. And so B is the first, so we will take B out and add A to the queue. So after it expands B, who is the first node in the queue? Who is the last node in queue? The first node in queue is who? Is C. Last node in queue is what? Is A. Okay. So it does this. So that's why we see the frontier is first in, first out queue. Okay. So this is the idea about breadth first search. So you do level by level. Okay. And then you can reach your goal. Okay, G. Okay, then next, let's see. So here we already discussed. Next is depth first. So let's take a look. So depth first it's opposite. It's expand deepest unexpanded node. So the data structure you want to go to deep. What kind of data structure we use for frontier? We use LIFO. What is LIFO data structure? What kind of data structure we use for LIFO? It's a stack. Okay, so last in, first out stack. Okay, so stack you can only access at the top. And here is that example again. Is it? So for the depth first search, so it will go along one path as deep as possible. So it will not do level by level. So we can take a look at this example again. So at the beginning, in your stack, you only have S. And then you get S out. You add its neighbor in. Is it? Suppose you add P, then you add E, then you add D. Assuming this is, you first add P, then E, then D. So D is the last node you add, but you will get it out first. So that's why here I'm going to expand D first. D first. And who are D's neighbor? D's neighbor is going to be B, C, E. Is it? So assuming you are going to add in the order of ECB. ECB. So now who is at the top? B. B is at the top. You get B out. You're going to expand B. So you're going to add A to the top. Okay. And A to the top, A doesn't have downward link. So you pop it out. And you go back to the stack. Who is next is C. So then you expand C. C's neighbor is who? Is A. So you expand, you need to put A in and then you pop A out. But A doesn't have any downward link, so you stop. And the next is E. So then for E, what you add, its neighbor is H and R. H and R. And then so for this one, you can clearly see it's go along the path as deep as possible, and then go back, and then expand its neighbor. So this is opposite from the breadth first search. So this is depth first search. And here is a example, or not example, here is a kind of cartoon said about depth first search. And sometimes if we apply this depth first search principle in our life, it can create some awkward situation. Okay, so after class, yeah, it's pretty funny. You can read it. So the next is so we discussed the search strategy. So how do we analyze the search strategy? So how do we evaluate? So generally speaking, when we evaluate the strategy, one consider the 4 aspects. Completeness. So the definition for completeness is what? Does the strategy always find a solution if there is one exist? So that's regarding completeness. Optimality. So optimality is it what? Does it always find the least cost one? Least cost one, just think about. So the depth first search, you just think, does depth first search give you the least cost solution? Depth first search. No. Is it? It will go deep, but may not be the least cost one. So depth first search will not always give you a least cost solution. Time complexity. So this is number of nodes generated. And the space complexity is the maximum number of nodes in memory. Okay. And for time and space complexity, we measure in terms of what? The following 3 terms. B, what is B? B is maximum branching factor of the search tree. Like you see, breadth first search, is it? It's branching. So the number of branching, so branching factor. D is depth of the optimal solution. So should be the least cost one. Okay. And M is maximum length of any path in the state space. In some cases, it may be infinite if you have a loop. So let's see. So property about breadth first. So is breadth first complete? Yeah, that means you can always find a solution. Yes, is it? But of course, it says branching factor should be finite. If you have unlimited branching, then there is no solution. So this is a complete. Is it optimal? Yes. And about time complexity, it's order of B to the D. B is branching, D is the depth of the optimal solution. And the space is also order of B to the D. So you can see regarding memory for breadth, it requires quite a large memory if the search state space is large. Okay. Yeah, so space is a big problem more than time. And then let's take a look at depth first search. So depth first search, is it complete? So regarding infinity depth, then all space with loops, then definitely no. Is it? But if not these two cases, then it is complete. Is it optimal? We just discussed no. Is it because what it returns, it may be a longer path than or the optimal. Because it returns the first path, deep path that it finds the goal, then it just returns. It won't do any further search. The time complexity. So it's based on the maximum depth. So it's B2 to the N. And the space. So the depth first search has an advantage regarding space because it's linear. It's B times F. So compare with depth first search and breadth first, it has the advantage of space. So then just think about, we just discussed the breadth first search and depth first search. So here the question is, can we kind of, so each one has their own advantage, that, so can we kind of like combine them together? That, so here is the idea of called iterative deepening search. What it does is it checks the root and it do the depth first search. It does depth first, but you limit the path length. You incrementally increment the path length. You won't let it always go to the longest. So the first you say, okay, path length is 1. So basically this is level 1. Path length, it's breadth first. You search of the shallowest. If you find it, okay, then you return. If not, you say, okay, I increment the path length to 2 by 1. So basically you do the second level. But within this length, you do depth first search. You follow the depth first. You don't do horizontal. So within the depth, you do depth first. But you limit, each time you limit the depth. So that makes sense? This definitely can improve the depth, can avoid the depth first search's disadvantage. Is it because maybe you have an alternate path that's shorter? Is it? So then in this case, you are not going to go all the way deep along one path. So you may have a chance to hit that shorter one. So this we call it iterative deepening search. So basically, it's you increase the path length and then do depth first search. So this kind of you have the good of both. Is it both sides? Okay, so here it gave us the idea about iterative deepening search. So the first is depth is 1. So in depth is 1, then you do depth first search for all of the nodes that has the depth of 1. If you cannot, you see, you increase the depth to 2. So regarding tree, the search tree, then you increase it to second level. If you still cannot, then you increase the depth to 3. And within each, you see, you still do depth first search. Okay, then let's see the properties of iterative depth first. So is it complete? Yes. You can always find a solution. Is it optimal? Yes. So in this case, opposite to depth first, you can find the least cost one. Okay. Time complexity. So this is branch. And this D is the depth. This depth. So the first time, the depth is 1. So that's why the branching 2 to the 1. Second one is branching 2 to the 2. Is it all the way to branching 2 to the depth? But this is polynomial. So the big O is still order of the highest order. So it's B2 to the D, okay. And regarding space is still linear. It's B times D, okay. Okay, then the next one, so the search, here we also assume the searching, the step cost. Search step cost it's the same, it's uniform, assuming it's always the same unit. But what if your step cost is different? Is it? So here's a breadth first for find the path with the fewest steps, but does not always find the cheapest path. So even breadth first and not always find the cheapest with varying step cost. That's why here let's discuss uniform cost search. So the uniform cost search. So previously you see, when we do breadth or depth, we don't consider the cost. We just consider the neighbor. Is it? And here, the key point is for frontier node, we also save what? Save the total cost of the path from initial to that node. Remember Dijkstra algorithm? It does this. Is it? You consider the cost. Okay, that's why we try to find the least cost paths. And then you expand frontier node with the lowest path cost. Then in this case, the frontier, what kind of queue? Then you cannot use queue or step. We got to use what? Priority queue. So in your priority queue, who is the first priority? Lowest cost one. Get the highest priority to get out of the queue, okay? And it says if all the cost the same, so the step cost is same, basically it's breadth first search. And if it's varying cost, then basic is digest algorithm. Okay, this uniform cost search. And we can take a look of this same one we do uniform cost search. So we have the starting state and the goal state. Is it? And initially in your priority queue, you have what? You have S. So you get S out. Okay, get S out. Get S out, you add it's 3 neighbor to the queue. So who will be at the front of the queue this time? Yeah, it's P. Is it? Because the cost from initial state to the current node is 1. It's the lowest. And what's going to be the second? D. The last is going to be E. So it's PDE in the queue. Because P is in the front of the queue, so you're going to take P out and expand it. So who is its neighbor? The neighbor is Q. So now for to Q, what is the cost to Q? So 1 plus 15, so that's why here it is 16. Okay, 16. So you add Q also to the Q. So right now in the queue, who is the front? It's 3. 3 is the front. Second is E. And the last is Q. Is it? So you have D at the front. So you are going to expand D. Expand D. D has neighbor B, C, and E. And if you add B, what's the cost from here through D to B is 4. And how about C? C through D is Y, that is 11. And E is what? Is 5. So now let's see. The Q has B, C, E, and Q. Is it? B, C, E, and Q. So who will be the front? Who is the first node in this queue right now? B, C, E, Q. Who is the first? B, C, E, and Q. Yeah, it's going to be B because B has the lowest cost. Who is next? E. Because E is the latest cost is 5. Who is next? It's C. And the Q, did you see, even though we added quite early, but it's pushed back to the Q because the cost is too much. That's why, so this search tree, so different color has the contour of the search space. Okay, so this makes sense? The uniform cost search, okay. Okay, so here it gives some other examples. And let's see the property of uniform cost search. So is it complete? Definitely. Is it? Because you can always find a solution. Is it optimal? Yes. Because the uniform cost, the goal is to find the least cost. And the time complexity is B, and C is cost of optimal solution. And divide by that epsilon. Epsilon is some step cost. And the space is also b to the c divided by epsilon. Okay. So what next? So we already discussed this 4 different search strategies. So let's take a quick look. Compare these 4 different search strategies. So breadth first search, is it complete? Yes. And is it optimal? Optimal means it always finds the best solution. Is if all steps cost the same, then it is. Time complexity is B2 to the D. D is the depth. Okay. Space is also order of B2 to the D. And depth first, is it complete? No, it will not always. And is it optimal? No. And time complexity is B2 to the M. M is the maximum path length. And the space is linear. It's B times M. And iterative depth search. So is it complete? Yes. You can find the solution. Is it optimal? Is that if all steps cost the same? Time complexity same as breadth first search. Space same as depth first search. So far it looks it's pretty good. This uniform or this iterative depth search. And the uniform cost search, is it complete? Yes. Is it optimal? Yes. And the time and the space complexity depends number of nodes. Okay. So here is the general idea about this 4 search strategy. Okay. And so which strategy you should adapt then depends on the problem and depends on what your goal is. If you want less memory, then you can think about like depth first search or like iterative depth search. And if your goal is least cost, probably you consider uniform cost search. Okay, so this is regarding the general search strategy. And next, let's take a look. The next part, so I need to do share screen. So we already discussed the search. And the last class, we discussed the tree search. So we initialize the frontier using starting node. And for the tree search is, if the frontier is not empty, you choose a node from frontier to expand. But according to what? According to search strategy. Let's ask you a question. For depth first search, the node to expand is what node? In frontier. It's the first node in the frontier. It's a queue. For depth first search is what? It's a stack. So basically, it's the last node you're going to expand. For that uniform cost search, which node? It's a priority queue. So it's get the highest priority node to expand. So that's why here it says, when you choose a node from frontier to expand, it depends on the search strategy. Okay. And if the node contains the goal state, then we don't need to continue. So we terminate the search. Otherwise, you keep expand the node and add its children. It add its children successor to the frontier node, frontier set. And the last class, we also discussed, we also needed to handle repeated state. That how do we handle repeated state? Is we keep an explored set. So you add a node to the explore set every time you expand the node. So for node you already expand, you add to the explore set. If the node already explore set, then you don't add it to the frontier anymore because you already expanded it. And then today we just discussed is what is N-informed search strategy. N-informed search strategy, we define it as pick the order of node to expansion based on the strategy. And we discussed the breadth first search, depth first search, iterative deepening search, and uniform cost search. Okay, so previously the discussion is about N-informed search strategy. And here we are going to start to discuss another topic. It's informed search strategy. It's informed. So you kind of have some idea, not like the other, you don't have idea. Here it's informed. So what that means? The inform means you have some hints about the desirability of different states. Yeah, you got some hint, but not the real cost. It's just some hint. Okay. And here says use evaluation function. So basically, we are going to use a heuristic. We call it a heuristic function. Okay, so the hint is a heuristic. Is a heuristic. Heuristic is just kind of, you have some hint, but not the real cost. And based on that, then you rank the nodes and you select the most promising one to expand. So this is different from that N-informed. Okay, so you base on some hint, then you rank the node to expand. And here we will discuss these two strategies. Greedy best first search. Second one is the A-star search. And in game design, we use the A-star search a lot. So let's see what are those. So you may also hear this a lot, heuristic. So what is a heuristic function? So heuristic function HN, it means it's estimate the cost to reach goal from the current node. It's just an estimation. That's why we say it's a hint. It's not the real cost. Okay. So it's an estimate. And here to give us an example, that like going to the maze. And then you have different states. But what will be the heuristic in this case? So normally in this kind of topology search, we can just use the straight line distance as the hint. Okay. Or Manhattan distance. So we will see. So here it gave us the next example. So if you recall last class, we discussed this example, is it? So we want to go from array to array go to some place here. I cannot remember clearly, but somewhere here. You breast, yeah. We are going to go to Burest. Yeah, go to here. Is it? And if you take a close look about this table, so what is this? Here it says straight line distance to Burest from array. Okay, and the number marked in that graph is not a straight line. It's some kind of cost, like your GPS, maybe that distance. That's different from straight line. Okay, from the straight line of 2 points. Straight line just Cartesian coordinate system, you can calculate that. Is it? But in the real world, there are a lot of obstacles. You cannot go straight line. Okay. But anyway, so this is a straight line. So let's see the greedy best first search, what it does, how it does the search. So it expands the node that has the lowest value of heuristic function. So in that case, which node is going to expand first? The lowest, the smallest straight line distance in its neighbor. Okay, so let's take a look. So here. So from array has 3 neighbors. It has these 3 neighbors. Those 3 neighbors, here we have the heuristic value. Be careful, okay? Those are heuristic value. This heuristic value is a straight line. It's a straight line. Okay, be careful. So there among these 3, which one is the lowest? Here you see, it is spew. Is the lowest. So you are going to expand the spew. And then you're going to expand spew. Spew its neighbor, it has 4 neighbors. And among these 4 neighbors, all done. So you compare 6 sockets. This is the smallest. So that's why next we're going to extend this. Okay, that's how it works here using heuristic. You see, we add them to the queue. Is it? And in Q, then we have the heuristic. Oh, basically here you already reach the purchase. But is this path the least cost one? No. It's not the least cost one in this case. Okay, but it's pretty good. You can see that. So this is you use a heuristic function to do the estimation. Okay, and here's regarding the discussion about the 4 properties: completeness, optimality, time complexity, space complexity. So complete, can you always find a solution here? It may not, because if you get stuck in a loop. Is it optimal? Here is no, we already see that. And about the time complexity, there is B2 to the F. And the space is also B2 to the F. So this is regarding greedy best first search, greedy best first search. And we see there's a problem. It's not completeness. It's not optimal. If it's not complete, not optimal, basically in the real world, it doesn't have a lot of sense. Is it? You must guarantee to apply something. You should complete and optimal. So how do we fix the problem? The greedy best first search problem. Here it says, you remember for digest search? Digest search, what we keep track of? We keep track of already visited distance. Is this here a similar idea? You can borrow that kind of concept. So we also keep track of the distance already traveled in addition to the remaining. That's what digesters does. Is it? So here we can kind of borrow that idea. So we can take a look in this case. So here, the total cost will be, so we have 1 from this initial to this current, add to the heuristic. So that's why we have 2. And the top one, why you get the number 3 is because the cost is 1, heuristic is 2. So that's why total cost is 3. And based on this 2, who you are going to expand? You're going to expand this node. So that's why you get to 3. Is it? And then you add, because it's tied, so you pick 1. So you get to 4. And the other one is also 4. And that's why you already reached the goal. Is it? So we can borrow this. So that's how we improve the greedy best first search is we do A star search. So A star search, the idea is avoid expanding path. That's already expensive. Okay, so here, the evaluation function this time is not just the heuristic, not just H. It's a sum of H and G. What is G? G is the cost to the current node, the actual one, actual cost. So in this case, you not only consider the heuristic, you also consider the actual distance. Okay, actual cost. So let's take a look at the example. So from array, okay, we are going to, it has 3 neighbors. So we add those 3 neighbors to the frontier. We add 3 neighbors to the frontier. Using each of the estimate who is 140. This 140 is the actual cost. That is the actual cost, 140. 253 equals 253 is what? is the Q. So in this case, this is the typical. This is the typical cost. And this is the so this is the cost. This is from the current. Okay. So then based on this three values, follow the lowest. This. That's why you're going to expand this. And then so we are going to expand the Cebu. And we expand the Cebu. Same thing. We need to come up, we need to calculate the estimation value. Estimation value is what? Is the actual cost plus what? Plus the unit. And when you have this 4 and this 2, you can take off the lowest. That's why this one is lower. So going to expand it. Who is it? The goal is to this one. You're going to expand it. Okay. So you're going to expand it. And after you expand this 3, then you get 8 of this node. Who has the lowest estimation value? Estimation value is what? Is the actual cost plus what? Plus that heuristic value. Okay, so you see the difference between this study and the previous we discussed that first. That's the minimum cost and the iterative deepening search. This is the difference. But this one some kind of similarity, like a diagram. But the difference from diagram usually here. But you can also consider what the cost to the current state. Okay, so that's the key point here. And we can keep doing like this. And then you can find the solution. That's it. And here to give some other example. And so the example shows about the A* search, how A* search works. Is it? So here's a couple of concepts, very important when we apply the heuristic. The first is called an admissible heuristic. So when you pick a heuristic, is it you can just pick anything? No, that won't work. So there's a condition for you to pick up the heuristic function. That's also the hard part for greedy algorithm. So what's the best heuristic function? Okay, how do we come up with heuristic function? So here the definition about admissible heuristic is, a heuristic is admissible. It must be for every node. Its heuristic must be less or equal than H*n. What is H*? H* is the actual cost. So your heuristic must be less than the actual cost. So for that array to Buchest, is that heuristic admissible? Yes, because it's a straight line distance. Straight line, any distance between 2 points, that's the lowest one. No one can be less than that. So definitely that heuristic is admissible. And here it says if the heuristic is admissible, then A star is optimal. So A star will give you the lowest cost solution. Optimal means lowest cost. Here. Okay, so this is just about A star. So very interesting. There are some issues here. So here it says based on that, A star can go wrong here. Yeah, why A star can go wrong? A star, if you so this is the star, this is O. And then so here we have that is 32. So A, this is the actual, this is the heuristic. So this part, and B is what? B is the actual plus the heuristic. So actual is around heuristic. This is, so you're going to go to B. You're going to follow B. Follow B. Okay, follow B and then to C. Same actual part from S, C, 1 plus 2. So this case is 1. Okay, you'll have this. And now we compare A and B. Because A is still from here. They haven't expanded. Between this two, who is this? This one is this. That's why you're going to so you already arrived at B. But is the actual cost only BCT is better? No. It's worse than the other. So here there's something wrong. And then the A star, that's why the A star, there's something wrong. So what's the problem here? So here, there is another very important concept. It's consistency of heuristic. Yeah, so if you want to guarantee optimal, you also need to make sure that the heuristic is consistent. And the consistency is stronger than admissible. Admissible is just heuristic. It's that is the actual cost. And that's admissible. But here, consistency is a different concept. What is that is the distance, the actual cost between two nodes, actual between two neighbor nodes. It must be two neighbors, parent and the successor, parent and child node. So the cost must be greater than or equal than what? The difference of heuristic. So A's heuristic is 4, A's heuristic is what? So the difference of the two heuristics is what? But the actual cost is what? It doesn't meet. That's why the problem comes up. So in that case, the heuristic themselves is not existing. So if heuristic is not an cost, so it won't be the outcome. Okay. So the consequence is that the F value along path never decreases. So estimate value if we have consistency, risk, then the estimate value should never reach it. Okay, and if your heuristic then is a practical, it's optimal. Okay, so this is a stronger condition. Okay. We can go back here. It says the F oh. What is F? F is that evaluation. That's the evaluation. So the cause and the heuristic. It should listen along the path. If it's an optimal path, it should never decrease. That's what if it's consistent. Okay. Then let's see. Oh, then you take a look. So is there something wrong? Yes. This is because it should never be. So that's why that's a problem. But if you can guarantee this, then you won't have that issue. Then it's optimal. Okay. Okay, optimality. And we can discuss this next class. Okay. So let's just stop here.